Let's continue working on this ENCOR lab. We are going to see the next topic, which is 3.1.c, configure and verify common spanning tree protocols, rapid spanning tree protocol, multiple spanning tree protocol, and spanning tree enhancements such as root guard and BPDU guard. So let's see some theory first, and then we're going to jump into the lab. Rapid spanning tree is an update over the traditional spanning tree. It is defined in AO2.1W. It still uses one topology with idle links, but with significant faster convergence times than the traditional spanning tree. So why do we need a spanning tree at all? Because we need to have redundancy in our networks. But with redundancy, the possibility of having network loops appears, so we need a layer 2 protocol that is able to logically put some port into blocking mode so we can break the loop. Now, what the spanning tree protocol actually does is taking your physical topology and calculate a logical topology in the form of a tree, where the root bridge is placed at the top of the tree. We are going to be able to configure several parameters like bridge priority, port priority, port cost, in order to do this selection of this root bridge and port roles. Some ports will be kept in forwarding mode, and other ports will be placed into blocking mode. So for all the ports that are in forwarding mode, that are pointing downwards in this tree logical disposition, are going to be named designated ports, and all the ports that are pointing upstream in this tree disposition are going to be called root ports. The root ports are the ports that happens to have the lowest root path cost. So these are the ports that provide the shortest path to reach the root bridge. By default, all the ports that belong to the root bridge are put into designated role. Now, when it comes to rapid spanning tree, we still have designated ports, we still have root ports, and but we have something new that is known as the alternate port. That is a port that is in discarding mode, but it is a particular port that provides a switch with an alternate path to reach the root bridge. And if we ever connect a hub to our switching domain, probably with two links, one link will remain in forwarding mode and the other link will be placed into discarding mode. That port particularly is known as the backup port. Now, when it comes to BPDUs, there are also differences. The original spanning tree will have the root bridge generate the BPDUs, and the BPDUs are forwarded by other non-root bridges. Whereas with rapid spanning tree, each switch is going to generate its own BPDUs. So the BPDUs becomes keep alives that let one switch know the status of the connection link and the adjacent switch. Now, rapid spanning tree has a process that is known as the proposal and agreement process. This process usually goes downstream, and it's usually initiated by designated ports. So if something happens in the network, there is a failure or event, and this network has to converge, proposal is sent only by designated ports. And that moment, several ports are put into discarding mode. So for instance, this is placed in discarding mode. This other switch places these ports in discarding mode upon receival of a proposal message. This happens only temporarily because this switch has to respond with an agreement message, and at that point in time, designated ports and root ports are placed back into forwarding mode. And then this switch, let's say switch number 2, has to start the process all over again. It's going to send a proposal message to the downstream switch. It will have to place this port in discarding mode. The last switch will do the same, and then this last switch has to respond with a an agreement message, and then these ports are placed into forwarding mode. Given this switch, let's say switch 3 does not have any other designated ports, the process stops there. If proposal message is not responded within certain time, that we assume that the proposal is considered to be expired. This is a summary of how it works. Now let's analyze how rapid spanning tree is better than the original spanning tree when it comes to convergence times. In this case, we are examining a local failure. In this case, let's call this switch 3. Switch 3 notices that there is a local failure. Its root port has become down due to a failure. In this case, with the traditional spanning tree, after the switch 3 notices that, it will have to transition its ports through the listening state, then to the learning state, to finally place them in forwarding state if it applies. So in this case, this port will transition from blocking to listening to learning to forwarding. That will take it 30 seconds to complete this process, because it stays 50 seconds in listening mode, 15 seconds in learning mode, for a total of 30 seconds in the case of a local failure. Now compare that with rapid spanning tree. In this case, switch 3 notices that this port went down, and then immediately it will turn its alternate port into the root port, and it will be placed into forwarding mode. So this usually takes less time than the usual original convergence time. Then this switch 3 has to go into notifying the rest of the downstream switches of a network event using a proposal message. So, however, but this switch does not have designated ports. So given this switch does not have designated ports, it will not get involved into creating a proposal message downstream. Now let's see what happens when convergence happens for a remote failure. In this case, let's go to this switch 3. Let's imagine that we have some device here that doesn't let switch 3 know that this other port went down. For instance, we have some DWDM infrastructure here, so this port remains up. So switch 3 will have to wait max 8 seconds before timing out BPDUs on this port. So it will have to wait 20 seconds before reaching the conclusion that something is wrong in the network, and at that point it will start transitioning its ports through the listening and learning states. So it will take another 30 seconds to converge. So in this case of remote failures, original spanning tree takes 50 seconds to converge, whereas with rapid spanning tree, in this case switch 3 will take 3 times the hello time to figure out that something is wrong, because it has stopped receiving hellos, BPDUs. So it will take 6 seconds to notice an event happened in the network. After that, it will it will start the proposal and agreement process for rapid spanning tree. This was a root port, but after it stopped receiving BPDUs that cannot reach switch 3 because of the failure, this root port becomes designated, and we are going to send a proposal message here. This port will be set in discarding mode, this as well, until a agreement is received. Given an agreement cannot be sent by this switch, the proposal message is going to expire. Then we are going to place these two ports into forwarding state. This becomes the root, and this stays as designated. In this case, this process is quite fast, so we can say that this process goes from 6 to 7 seconds. Compare that with 50 seconds in the original spanning tree protocol. Now, when this port normalizes, switch 3 will receive a proposal from the root bridge, and this means that these ports will be placed in discarding state for a moment. Then an agreement is sent back from switch 3 to the root, and then these ports are placed in forwarding mode. This port will remain discarding because it is the new alternate port. Given switch 3 does not have any designated ports anymore, the process ends there. It will not send a proposal to any other switch because it doesn't have any designated ports. So let's see now the summary of differences between rapid spanning tree and multiple spanning tree and old spanning tree. Remember that multiple spanning tree is actually an extension of rapid spanning tree. It is basically using the same protocol, but it will provide several topologies, but it is basically the same protocol. Now, when it comes to port states, the original spanning tree had disabled, blocking, listening, learning, and forwarding. Rapid spanning tree and multiple spanning tree only have discarding, learning, and forwarding modes. When it comes to port roles, the original spanning tree protocol had the root port and designated ports, whereas rapid spanning tree and multiple spanning tree have root port, designated port, alternate port, and backup port. When it comes to BPDU creation with the original spanning tree protocol, the root switch creates BPDUs. And for rapid spanning tree and multiple spanning tree, each switch generates its own BPDUs. When it comes to the flags field within the BPDU header, the original spanning tree will only use 2 bits, the topology change bit and the topology change acknowledge bit. Whereas in rapid spanning tree and multiple spanning tree, we used all of the bits for several stuff. We still use TC and TCA for backward compatibility, but we have the proposal bit, the agreement bit, and so on. When it comes to convergence process, the original spanning tree protocol uses max age timeout and listening state, learning state, and so on, transitioning the states. Whereas with rapid spanning tree protocol, we use a pair of switches, handshakes, proposals, and agreements. Now, remember that in order to select port roles such as the root port, designated port, and alternate port, we use the cost of the one of the parameters is cost, another is priority. But cost will assign a certain weight or value to an interface depending on the rate. We have the traditional cost that we are going to call the short mode cost, that is efficient up to when an interface is a 20 gigabit per second interface. That in that case we reach to the the lowest cost value, and we cannot go any further. So for instance, if we had a 100 gigabit per second interface that is better than a 20 gigabit per second interface, we should we can only provide that interface with a value of 1. So we have a technological limit here. Now, in the early 2000s, the standard AO2.1t publishes this possibility to have a long mode. A formula applies here in order to calculate the new cost, and this long mode allows to assign cost to interfaces up to 2 terabytes per second. By default, multiple spanning tree uses long mode. Now the question is if I am using rapid spanning tree, what mode will my switch will be using by default? So that will depend on how old is your switch or how old is your operating system. In the case of Catalyst 9000, if you have an iOS XE up to 17.2, it will use short mode by default. If you go with operating system higher than 17.2, chances are high that your Catalyst 9000 will use long mode by default. Now, the best practice here is you have to make sure that the same mode is used across the switching domain for consistent spanning tree calculations. So either all your switches are going to go for a short mode, or all your switches are going to use the long mode. So you can configure that with the global config command, spanning tree path cost method, long or short. Now, this is a rapid spanning tree thing which classifies link types. We have shared, point-to-point, and edge. And these two ones, point and edge, will use rapid convergence, and shared links will use all traditional convergence. If your switch is unable to detect that you have, for instance, a point-to-point link, you can configure that manually using the command spanning tree link type point-to-point, for instance. This happens usually on all switches. More recent switches are able to detect these link types. So for instance, if we had this topology, this link here will be a point-to-point link, this link here will be a point-to-point link, this link here will be a point-to-point link, this will be an edge link. If you have an old switch, you have to make sure that these link types are detected correctly, because these link types will execute the AO2.1W or rapid spanning tree convergence process. This hub here is going to be classified as a share link, and this particular link will use traditional AO2.1D convergence process. Now, CISCO offers a way to use rapid spanning tree, but CISCO will not offer you the plain vanilla standard rapid spanning tree. CISCO will offer you with a particular version known as per VLAN spanning tree. So it is known as rapid per VLAN spanning tree plus. With this particular CISCO version, you have one topology per VLAN. Remember that the original rapid spanning tree only offers you one topology. So with rapid per VLAN spanning tree plus, you have one topology per VLAN. That has the advantage of avoiding idle links and the disadvantage of generating too many BPDUs and plus the original BPDU. For instance, if you had 20 VLANs, CISCO per VLAN spanning tree will be creating 21 BPDUs every 2 seconds. And if something happens with your network, your switches will be calculating 20 spanning tree topologies. In order to select this protocol, you have to enter the command spanning tree mode rapid RPVST. Now, this will be basically the difference between vanilla, plain, normal rapid spanning tree and CISCO's rapid per VLAN spanning tree. For instance, rapid spanning tree protocol, the original AO2.1W, will only offer one topology. So it will place one port in discarding mode for all VLANs. So this has the disadvantage that this link will be idle and wasted and not used. So, but with rapid VLAN spanning tree, you can generate one topology for VLAN 10, one topology for VLAN 20, one topology for VLAN 100, and one topology for VLAN 200, and so on. So you will have one topology per VLAN where you can set up a priority, different priorities, different costs for your port or your switches depending on the VLAN. So for instance, for VLAN 10, this is the root bridge. For VLAN 20, this is the root bridge. For VLAN 100, this is the discarding port. For VLAN 200, this is the discarding port. This has the advantage that you don't have idle links. For VLAN 10, you will be using this link. For VLAN 20, you will be using this link. For VLAN 100, you will be using this link. For VLAN 200, you will be using this link. So you are not wasting links that remain in idle mode. Now, when it comes to BPDUs, the original rapid spanning tree protocol only will use one BPDU, whereas with rapid per VLAN spanning tree plus, you will be using several BPDUs. You have to be aware of that. Now, when using rapid per VLAN spanning tree plus, an issue comes up. With the original AO 2.1d, you could set up a switch priority using this 16-bit priority number. So you could use these values, but when using rapid per VLAN spanning tree plus, you must specify to what VLAN this priority is being assigned to. So we are going to steal 12 bits from the original 16-bit priority field in order to store the VLAN number. So that leaves us with a priority of 4 bits only. With 4 bits only, we can establish these values. These values are established in 4096 steps. So if you go for the first value, you have to multiply that by 4096. So the first value that you can establish will be, besides 0, will be 4096, and you can go from there up to this number. So be aware that we are using less bits to establish the priority. So this is known as extended system ID. For all switches, you have to enable this behavior with this command, spanning tree extended system ID, but for recent switches it is enabled by default. Now, when setting up the priority for a certain switch, you have to establish then to what VLAN or what VLANs this is going to apply to. And the same applies for every single configuration that you are going to perform on your spanning tree. If you want to establish which switch will be your primary or root switch and your backup primary switch, if you want to modify your port priority, your port cost, your halo time, your forward time, your max age, you have to establish to what VLAN are you applying this change to. Because remember, you have topologies per VLAN, and using these commands you are actually creating different topologies with different settings for every single VLAN or VLAN range. Now, in order to validate your configuration, you can use show spanning tree. In the case of rapid per VLAN spanning tree plus, and this output will be shown for every single VLAN that you have. Remember that every single VLAN has a different topology. So if you had 20 VLANs, this output will be multiplied by 20, and the output tells you to what VLAN this output belongs to. In this case, VLAN 1, and then you will be shown VLAN 10 and VLAN 11 and VLAN 20 or whatever VLANs you have. Now, it will tell you what protocols are you using. In this case, RSTP tells you that you're using AO2.1W. Now, it will then give you information about the root bridge and about the switch that you are working on right now. It will tell you the priority of the root bridge, the MAC address of the root bridge, and then in this particular example, the bridge that you are working is also the root bridge. So this information repeats because it turns out this is also the root bridge. So this information is the same in this case. Notice that the actual priority can be calculated by subtracting from this value the VLAN number, because remember that the original priority had 16-bit and we have to steal 12 bits from that. The 12 bits correspond to the VLAN number, so if we subtract this, the VLAN number, which is 1, we end up having the actual priority for this switch. Now we then get enlisted the amount of ports that are participating in spanning tree, the port role. Remember that the rule for a root bridge is that all of its ports will be put in designated role, because they are pointing downstream in the logical spanning tree. So they all will be placed into forwarding mode. We are using the short coast mode. Looking at these values, this is the port priority and the link type. Now this is a distribution switch. Notice this is a distribution switch and this is an access switch. So we can also issue this command, and we will see, for instance, that this is not longer the root bridge, but this value is telling us the root path cost. So how far are we from the root bridge? In this case, when we see that it's a value of 4, we can conclude that this switch is connected to the root bridge by 1 gigabit per second interface, because for the short mode cost, 1 gigabit per second interface have a value of 4. So with the output of show spanning tree, you can begin to actually draw a diagram of or how your network is connected. Now regarding this last column, which gives you the link type, we can see these link types that are the original A02.1W link types: shared links, edge links, and point-to-point links. We can see others. For instance, if we were configuring one switch with rapid spanning tree protocol, and these were connected to a traditional A02.1D, we will see this port reporting bound STP, because we are seeing a traditional original rapid spanning tree protocol switch. Now if we were configuring an multiple spanning tree protocol border switch and we were connecting this to a rapid spanning tree protocol switch, we will see in this port this link type: point-to-point bound to rapid spanning tree protocol. So in this case, a multiple spanning tree border switch is seeing a rapid spanning tree protocol switch. And if we were connecting a switch that in this port is operating in trunk mode and this other end is in access mode, you will see this mismatch trunk access. Typing on system mode, and this port will be placed in discarding mode. These other link types, we will see them later on. And that's it. These are the rapid spanning tree features that we saw: port states, port roles, long and short metric type, link types, the convergence process. And regarding per VLAN spanning tree plus, we saw what is the extended system ID and how to configure and verify rapid per VLAN spanning tree protocol. Now let's see the next topic, which is multiple spanning tree. Multiple spanning tree is a standard protocol defined in A02.1S. provides separate instance-based topologies. Each instance will run AO2.1W. So it is actually an evolution of AO2.1W, but with different topologies. So if we wanted to compare how multiple spanning tree compares with CISCO rapid per VLAN spanning tree protocol plus, we will see this. MST offers us the possibility to create instances. So in this case, I will create this instance where this is the root bridge and this is a discarding port, and I can create another instance where this is the root bridge and this is the discarding port for the same physical topology. In this case, I only have 2 topologies to calculate if everything goes wrong. Whereas with rapid per VLAN spanning tree protocol, we can define 1 topology per VLAN. So in this case, for VLAN 10, this is the root and this is in discarding mode. For VLAN 20, this is the root and this is in discarding mode. For VLAN 100, this is the root and this is discarding mode. And for VLAN 200, this is the root and then this is discarding mode. Notice that we are repeating our topologies. This is not very efficient because in this case we have 4 topologies. And these topologies can be mapped to only 2 topologies if we were using multiple spanning tree. So in that case, multiple spanning tree is more efficient. These particular topologies are known as multiple spanning tree instances. So in this example, we have this MSTI and we have this MSTI. 2 different topologies for 2 different instances. Now, regarding BPDUs, MST only uses 1 BPDU. 1 BPDU for all your region. So this BPDU is handled by something that is known as the instance 0. When you configure MST by default, you have instance 0. You cannot delete instance 0. Instance 0 exists on all your switches. It exists on all your ports. You cannot get rid of instance 0 because instance 0 represents a topology. This topology represents a whole MST region. And this particular instance only uses 1 BPDU. Only 1. Compare that with rapid per VLAN spanning tree plus that will send 1 BPDU per VLAN plus 1 traditional BPDU AO2.1D every 2 seconds. So if you had, for instance, 4 VLANs, you will be sending your traditional BPDU plus 4 other BPDUs every 2 seconds. So in that case also multiple spanning tree wins at being more efficient. Now just another note about instance 0. Instance 0 creates 1 topology that is known as IST, internal spanning tree topology. So this IST is the topology for the instance 0. As we had MSTIs, for instance, MSTI 1 for instance 1 and MSTI 2 for instance 2 and so on, we have EST for instance 0. So this is the instance 0 topology. It is known as internal spanning tree. This will send BPDUs, as we saw in the previous slide. These BPDUs will include M records that contain all the information in order to calculate all the MSTIs within this domain. So a multiple spanning tree is so efficient that it only requires one BPDU, and within this BPDU that is controlled by the IST or internal spanning tree contains M records that contain enough information to calculate your multiple spanning tree instances topologies. So, summarizing the comparison between MST and rapid per VLAN spanning tree, we saw that MST is a standard protocol. The rapid per VLAN spanning tree is not a spanning tree protocol. Rapid per VLAN spanning tree has one topology per VLAN. MST has one topology per instance, so it is more efficient. Multiple spanning tree will calculate less spanning tree topologies, so it is less CPU intensive than rapid per VLAN spanning tree plus. Rapid per VLAN spanning tree plus transmit one BPDU per VLAN plus a CST BPDU, whereas multiple spanning tree transmit only one PDU. So in that sense, multiple spanning tree is more network efficient than rapid per VLAN spanning tree plus. In order to select MST as your spanning tree protocol, you should issue this command, spanning tree mode MST. Now, MSTs are configured by regions. So an MST region is a set of switches that agree on one configuration identified by a region name. So you go into configuration mode, spanning tree MST configuration, and issue the command name to set up your region name for a set of switches. Several regions can coexist, each one identified by your region name. So that means that in your switching domain you can have several regions. Each one is identified by a region name. So in this case you have this region name foo. So this switch is configured to use region name foo, these two as well, and these two as well. Now this other region is named bar, so this switch is configured to belong to region bar, bar, and bar. Remember that each region is represented by instance 0. Instance 0 has a topology known as the internal spanning tree. So this region name foo has one IST, and this region bar has one IST. And so you might wonder why this is becoming so complex, and you must remember that in the late 90s and early 2000s, the campus design was a layer 2 design. So everybody was deploying large layer 2 campus networks, and they were usually suffering from a lot of layer 2 loops. And these protocols were created with that in mind. We don't design these networks anymore this way. We usually have a small layer 2 domains connected to layer 3 networks, and then we grow on the layer 3 part of our network. So however, if we think about how networks were deployed in the late 90s and early 2000s, this way of dividing your network makes a lot of sense. So let's just summarize what we talk about MSTIs. Multiple spanning tree protocol lets you create instances. Some CISCO switches only let you create 1 to 15, but these change depending on your switch capabilities. Each instance has its own topology. Idle links are eliminated, and load balancing is possible. VLANs get assigned to instances. By default, instance 0 has all VLANs, and remember that MSTIs have are scoped by region. So for instance, if you're using instance 5 in one region and you're using also instance 5 in another region, they are completely different, separated. They don't have to do anything with one another. So in order to create an instance and assign it VLANs, you go into spanning tree MST configuration, and then you issue instance the number of your instance and the VLANs that belong to that particular instance. Now, this is for example of how you have two regions. So you have this region named foo, and you have instance 1 that has this topology and instance 2 that has this topology. And in another region, you have also instance 1 that has this topology and instance 2 that has this topology. So this instance 1 has nothing to do whatsoever with these other instance 1s. They are not related. They just happen to have the same number, but they belong to different regions. Bear that in mind. Now, how do you configure multiple spanning tree? You can configure different priorities, different costs to your switches and to your ports, but you have to establish to what instance you are trying to change these parameters to. So remember just to issue a spanning tree, MST, the instance number, and the parameter that you want to change. So for instance, to change or to set up what will be your primary root bridge, you will issue a spanning tree, MST, and then the instance number where this bridge will become the root bridge. Now, this is a summary of how complex can your multiple spanning tree deployment can become. Remember that, as I said previously, multiple spanning tree was created when everybody was deploying large layer 2 networks. We don't do this anymore. If you have this complexity in your networks and you design it, you are something doing wrong. But probably you are managing an old network that cannot be upgraded for some reason, and then you might probably want to do this. You might want to create your regions. Remember that each region has its own IST. IST is the topology that corresponds to instance 0. So you have instance 0 in each region. Remember that you cannot delete instance 0. Instance 0 has the topology that is known as internal spanning tree. This internal spanning tree represents your region. The topology that belongs to IST represents your region. You can also have your several other MSTIs at each region. They are independent of each other's. So you connect your regions through CIST regional routes. So this switch will become the CIST regional route because it is connecting this region to this other region. And in this case, this particular region X has a CIST regional route that happens to be also the CIST route. That means that this is the root of the whole domain. And CIST is a collection of regions. So I hope this makes sense. Now, two final recommendations when it comes to designing multiple spanning tree. You have to be really careful when using the command allowed VLAN with multiple spanning tree. Allowed VLAN and multiple spanning tree are not really friends. So you have to be really sure about what you are doing if you are filtering VLANs on your links, if you are using MST. Let's put this example we have this instance 1 that has attached VLAN 10 and 20. So for this instance, this port is set into discarding mode. This is not the correct name. This is discarding. Remember that we are using internally rapid spanning tree. So that means that VLAN 10 and VLAN 20 are going to use this link to transmit frames. But if by mistake you enter this command into this trunk port allowed VLAN 10, you are actually crippling VLAN 20. because only VLAN 10 can transfer frames in this port. So where are going to the VLAN 10, VLAN 20 going to get transmitted through? Remember that this port is in discarding state, so we are not able to use this link at all. So if you filter VLAN 20 out of this trunk, you're actually making VLAN 20 discontiguous. You will have VLAN 10 devices here and VLAN 10 devices here that will not be able to communicate with each other because you just filter out VLAN 20 from this trunk here, and the frames cannot travel here because this port is in discarding mode. Be aware of that. Now when you're configuring your MST region or MST domain, you will have border switches, and if you are connecting these border switches to for instance a switch that only manage rapid spanning tree or rapid per VLAN spanning tree plus, your whole MST domain will behave as a really huge switch. So this other switch will see that it is connected to a really huge switch, and MST will behave as a really huge switch to the outside world. In this case, you have two options. You can use this big switch to be the root for all VLANs, or you can choose to be non-root for all VLANs. You only have two options. You don't have a middle ground here. You cannot choose VLAN 10 to have a root switch inside here, and VLAN 20 to be this switch, and VLAN 30 to have a root switch inside this MST region, and VLAN 40 to have a root switch, this switch. So you cannot mix that. You should choose to have all the root of your VLANs should be inside your MST region, or you can choose to be a non-root for all VLANs. So there are other features that we are not discussing here. For instance, boundary ports and subregions. Now, in order to troubleshoot your or verify your multiple spanning tree protocol, you can use this command. In this case, you may see this if you are connecting your MST domain through a border switch connecting to per VLAN spanning tree plus switch. You are going to see this when issuing this command, P2P bound PVST. Now, when issuing this command, you're going to get this output for every region. So if you have 4 regions configured by you will see this output multiplied by 5, because you are going to be shown first the MST 0 for instance 0. Remember that this is the IST or internal spanning tree topology, and then this command will show you all your topologies that correspond to other instance 1, instance 2, instance 3, instance 4, and so on. So for this particular instance, we are running MSTP, obviously, and then it will show you the information that regards to the root bridge for this particular instance and the switch you are working on. In this case, this is a distribution switch that happens to be the root for this particular instance 0 or internal spanning tree instance topology. So remember that all ports that belong to the root bridge are always put in designated mode. They will be forwarding. Notice that we are using long mode for the cost. Long mode is used by multiple spanning tree always, and this is the priority, and this is the link types for these ports. This is the same output for the other distribution switch. Notice that it is 20,000 units away from the root bridge. So with this output, you can start drawing your diagram. Remember that 20,000 is the number or cost that is assigned to 1 gigabit per second interfaces for the long mode. And you have all the ports that are participating in MST0 and the role, the state, the cost, the priority, and the link type. Now you can use this other command, show spanning tree MST. Remember that the previous command was show spanning tree. You can use show spanning tree MST. If you want to go deeper into MST, it can tell you which one are the CIST roots and what are the regional root switches. Now, this is the summary for MST. We saw what is the LAN metric, rapid 3 port states, because MST actually uses AO2.1W for every instance. We saw what are regions name, multi-regions, what is an instance, how BPDUs contain M records for all instances, what is the difference between multiple spanning tree instance, internal spanning tree, CST and CIST, which is the CIST root, and which one is the CIST regional root. How do we interconnect multiple spanning tree to traditional spanning tree and per VLAN spanning tree? We didn't see this on the reports and subregions. Now let's go for the last part of the theory. Here we're going to see spanning tree features, root guard. What you want to do with root guard is actually prevent people from connecting a switch that will try to become the root of your spanning tree protocol. Remember that we usually have 2 distribution switches and access switches, and you choose which one will be your root. Usually you will pick one of your distribution switches as the root because this switch is huge. It has a lot of capability to switch packets, and all the traffic is going to go through this switch, and it is highly capable of moving this traffic. But what happens if a user connects a switch that happens to have a priority set to 0? Then, given this switch has priority 0, it will try to become the root of your spanning tree topology. This will wreak havoc in your network because now all traffic will try to go through this switch. This switch is not capable of handling all this traffic. Your network, your whole layer 2 network will go down in seconds. So this can be considered to be an attack, or can be the source of an employer that doesn't know anything about the spanning tree and just plugs in a switch. So if you use root guard, this port here will be placed in root inconsistent state. So this is the way to configure that. For a certain interface, you enable spanning tree guard root. Then if someone plugs a switch that wants to become the root switch for your network, this is the alert that you will see: spanning tree root guard block, root guard blocking port gigabit 02. And if you issue show spanning tree, you will see that this port will be placed in discarding state, and you will see that the link type is set to point-to-point root inconsistent mode. Now, when the offending switch is no longer sending better BPDUs, probably someone got in and configured it to a higher priority, the port is cleared, you will receive this message: root guard unblock, root guard unblocking port gigabit 02. you will see that this is in designated role, forwarding, and now it is P2P. Now we have also loop guard. Loop guard will help you be sure that your alternate port is actually providing a good alternate path to reach a root bridge. So remember that you have this topology with 2 distribution switch and 1 access switch, and this port can be set into on discarding state, and it becomes the alternate role. You have a root port where traffic is coming and going, and you have this alternate port. And this alternate port, when everything is working correctly, is continuously receiving BPDUs from this other distribution switch. It is every 2 seconds this distribution switch is sending BPDUs to your access switch. And the alternate port is considered to be healthy because everything is working normally. But what happens if for some reason you stop receiving BPDUs on this alternate port? If you don't use loop guard, this alternate port is actually not providing a healthy alternate path to the root bridge. So with loop guard, if you stop receiving BPDUs on an alternate port for some reason, this port will be placed into loop inconsistent state. So if you configure that in some interface and you stop receiving BPDUs, you will see this message: loop guard block, loop guard blocking port wherever. And then if you issue show spanning tree, you will see that it is in discarding state, and the link is classified as point-to-point loop inconsistent mode. Now, if BPDUs come back, the port is restored. You will see this loop guard unblock, loop guard unblocking port, and you will see this message. There are other features for spanning tree. For instance, you can have BPDU guard. If you enable that in a port and you connect a switch, so this port will become will be put in error disabled state. So you might configure that on ports that go to end users, probably to connect printers or laptops or desktops, and you don't want a user to connect a switch there. That is forbidden. So you enter BPDU guard, and as soon as this switch sends the first BPDU, this port is set into error disabled mode. So for instance, you can configure this in this way: BPDU guard enable. This is the alert that happens when someone plugs in a switch there, and if you issue show spanning tree, the port will not show up because it is down, because it was set to error disabled mode. So in order to normalize it, you will have to go actually in there and reset your port. Even if the user disconnects the switch, the port will remain in error disabled mode. Now, other features: port fast. And if you enable port fast, your port transitions to forwarding state, skip and listen and learning states. And with BPDU filter, your port no longer sends BPDUs to the outside world. So this is a summary of your spanning tree features. The loop guard will apply to alternate ports. It will make sure that your alternate ports are healthy and are receiving BPDUs. Root guard will prevent you with against rogue root switches. BPDUR will prevent you from getting rogue switches getting connected to your network. Port fast will make your ports available faster for the end user. Otherwise, the user will have to wait about 40 seconds before the port becomes available. 30 seconds. BPDU filter will stop sending or transmitting BPDUs to the outside world. So let's jump into the lab. We are going to configure MST here with the help of BTP version 3. We are going to configure here rapid per VLAN spanning tree plus. We are going to configure 2 instances here. Instance 1 will put this port in blocking mode, and for instance 1, switch 3 will be the root switch, and instance 2 will place this port into discarding state, and for instance 2, switch 4 will be the root switch. And we are going to do the same here for VLAN 102. This port will be in blocking state, discarding state, and this switch will be the root. And for all other VLANs, VLAN 100, VLAN 101, and VLAN 10, we are going to place this port in discarding state, and this will be the root for the spanning tree protocol. So let's configure that. So let's go to switch 3. Switch 3 should be my my server, but we don't have anything for MST. I'm going to enable MST for BTP, so BTP mod server for multiple spanning tree. Let's go to the other distribution switch, show BTP status. In this case, BTP is not working for MST, so let's configure that. BTP mode MST server for MST, and the access switch show BTP status. So in this case, MST is in transparent mode, so let's put it in BTP mode client for MST. So in this way, what I am doing is setting up BTP, so I have only to configure MST once, and the all other switches will get the configuration. So in that way, I avoid sending or configuring the same MST configuration instances at every single switch. So I have to do it only once. So let's see who is the primary server for MST. There is no primary server, so I have to issue BTP primary MST so I can start configuring. Remember that for version 3, BTP version 3, even if you are a server, you cannot do anything unless you are the primary server. So in this case, I am enabled switch 3 to become the primary server for the domain for configuring MST. So if I issue show BTP status, okay, now I am primary server and I am in BTP server mode for MST, so I can now work with MST. I'm going to check if I am running MST, so spanning tree. I am using the traditional original spanning tree protocol. So the first thing I'm going to do is configuring MST, spanning tree mode MST. So I am choosing now MST as my spanning tree protocol. If I issue show spanning tree again, I can see that I am using MSTP now. Let's do that here. Show spanning tree. This switch is still using traditional spanning tree, and let's issue show spanning tree here. This switch is using traditional spanning tree as well. So what happens if I issue show spanning tree? I have to see something particularly in the link type. It is taking some time. Let's remember that this emulation is a bit slow, and we are still in the learning state. We have to wait until reaching the forwarding state. Okay, we can see that we are bound to per VLAN spanning tree. So this means that we are running per VLAN spanning tree on the other side. Let's this is port channel to switch 4. Hold on a second. Okay, the connection was restored to my GNS3 server. So let's configure multiple spanning tree on axis A and distribution switch 4. Okay, let's go to axis A and let's issue a spanning tree mode MSTP, and then comes the spanning tree mode MST. So I'm using multiple spanning tree mode in my 3 switches, and let's now issue show spanning tree here. Now I can see P2P everywhere. Notice that we are using long mode costs by default because MST uses long mode by default. This port channel receives a better cost, and this other port channel receives even a better cost because this port channel 34 it should be 4 gigabit per second. Port channel 35 should be 2 gigabit per second, and these other interfaces are 1 gigabit per second. So that is why we are receiving different port costs. So show interface port channel 34. Its bandwidth is set to 4 gigabit per second because it is bundling 4 interfaces together. Okay, so let's configure MST, and we are going to issue a spanning tree MST configuration. We are going to set up first the region name. We're going to call it lab, and then we're going to configure instance 1 that will belong to VLANs 10, which is my management VLAN, VLAN 100, which is my user VLAN, and 101, which is my voice over IP VLAN. And then I'm going to create instance 2 that will only hold the guest VLAN, which is VLAN 102. So if I issue show spanning tree MST configuration, I will see this. Instance 0 exists by default. I cannot delete it. It by default is linked to all VLANs, and as I start attaching VLANs to other instances, we are withdrawing these VLANs from this list. I cannot delete instance 0. The topology for instance 0 is known as internal spanning tree, and this internal spanning tree topology represents my region. My region name is lab. So let's see what happens here at switch 4. Show spanning tree MST configuration. And I didn't configure MST here, but given I am using VTP version 3, VTP made sure to inject this configuration automatically. So let's see now. Show spanning tree MST config, same configuration. So let's issue, for instance, show spanning tree to see how my what interfaces am I blocking. So for I am interested in instance 1. Instance 1 is blocking the port channel that goes to switch 3. So probably switch 3 is not my root switch for instance 0. So let's see. Show spanning tree instance MST instance 1. It seems that this is not the root bridge for instance 1. I should see here this switch is the root bridge. So I want switch 3 to become the root switch for instance 1. So I have to issue another command. Spanning tree MST for region 1. I want this to become the root primary. And for the same region, I want this other switch, spanning tree MST region 1 root secondary. I want my distribution switch to be the root primary and root secondary. In this case, for instance 1, the root is this switch. So that is what I wanted. In this topology, for instance 1, this bridge is the root. And if we examine here how the instance 1 is working, we can see that the port channel that goes to switch 4 is in blocking mode. It is the alternate role. So that is what I wanted. Now let's see what is going on with the second region. Let's see here. For the region number 2, I want switch 4 to be the root bridge. Probably it is now. In that case, okay. For region 2, I have not configured anything yet, but this is the root bridge just by luck. But I don't want that luck runs this network, so I have to configure that manually to be sure that this always be my root primary for instance 2. So spanning tree MST region 2, this will be the root primary. And I actually don't want access A to ever become a root, so the root secondary will be switch 3. So spanning tree MST for region 2 root secondary. So far so good. Now we could set up some other features. Let's go to Nexus 3 and Nexus 4. MST is complete now on this side of the network. Let's go for Nexus 3 and configure per VLAN spanning tree. And Nexus 4 as well. We're configuring the green network in the diagram. We are going to use per VLAN spanning tree. So if I issue show spanning tree here, we are already using rapid spanning tree. So we want to configure this in such a way that for VLAN 10, 100, and 101, this will be my root primary. And Nexus, no, sorry, I'm configuring Nexus 4. I want to enter this in Nexus 3. So Nexus 3 will be my root switch for VLAN 10, 100, and 101. And for VLAN 102, This will be the primary route. Now, let's configure this as the backup for VLAN 102. This will be root secondary. I am doing this so I am sure that my distribution switches will be always the root. I don't want my access switch under any circumstance to ever become the root switch, so I am setting up root primary and root secondary. So okay, so if we issue show spanning tree for VLAN 10, okay, I have to create VLAN 10. This is a leftover from a previous lab, VLAN 100 to 102. Okay. Now this bridge is the root for VLAN 10. My port channel is now in blocking mode, and okay, let me create the VLANs here. Okay, VLAN. My VLANs are not created yet, so I have to create them. If the VLANs are not created, spanning tree will not kick in. Now let's see. Okay, now this bridge is the root for VLAN 10. All of the ports are designated. Remember, this is the rule. For VLAN 100, this bridge is the root. For VLAN 101, this bridge is the root. And for VLAN 102, this is not the root bridge. So for 102, this bridge is the root. This is not the root for VLAN 101. This is not the root for VLAN 100. And this is not the root for VLAN 10. I should see another port here, Ethernet 1.4. Ethernet 1.4 is not configured yet. So let's configure Ethernet 1.4 switch port mode trunk, switch port trunk, native VLAN 323, and switch port trunk allowed VLAN 10, 100 to 102. No, shoot down. Okay. I can see now Ethernet. This is the interface that goes to the access switch. That is why I have to configure it. So for VLAN 10, for some reason it is blocking. Let's see access. Show spanning tree. Oh, this one is using, sorry. Let's see this. Access B. We are still configuring the green network. Okay, now spanning tree here, we have to enable it. Spanning tree mode, rapid per VLAN spanning tree. Okay. Now show spanning tree VLAN 10. Gigabit 1 is forwarding and gigabit 2 is the alternate port. That is correct. I am watching this part of the network here. VLAN 100, gigabit 1 is the root, gigabit 2 is the alternate. Gigabit 101, gigabit 1 is the root, gigabit 2 is the alternate. This should change. In this case, for gigabit 2, for the VLAN 102, gigabit 2 is root, and gigabit 1 is the alternate port. Notice the difference between this, root and alternate and root. This is because the switch 4 is the root switch for VLAN 100 Nexus 4. Nexus 4 is the root for VLAN 102. So in this case, gigabit 2 is closer to the root than gigabit 1, so gigabit 1 becomes alternate port for gigabit for VLAN 102. So these are the priorities. Notice that this is the root primary for region 1 and root secondary for region 2. And this one is root secondary for region 1 and root primary for region 2. What else? What if we show a spanning tree MST? So it seems that this is not a regional root. If we show a spanning tree MST, this switch is the root for the whole domain. This will matter if we had several regions, but just in case you have several regions, you could use show spanning tree MST to know which switch is your regional switch, which one is your CIST root switch, and so on. So so far so good. Okay, that's it.